Today's lecture essentially is essential for for the whole of the rest of the course, because today we'll essentially be talking about Newton's second law, and that of course is used basically throughout the rest of the course. Okay, so pay attention. Okay, it's okay if you're not able to understand everything that I'll babble today. Okay, but think about it. Okay, and make sure you get it after tomorrow. Okay, because I know you are busy revising projectile motion and relative velocity today, as you won't be thinking about Newton's laws today. After the trauma tomorrow, just think about Newton's second law. Okay. Okay, so last time, remember, we talked about Newton's first law, and Newton's first law sets the stage for Newton's second law. The whole idea of Newton's second law is that forces or interactions lead to acceleration. So if an object overall is interacting with something else, it should be accelerating. Okay, if the net interaction on an object is non-zero, that object should experience non-zero acceleration. Okay, and we saw that this idea really is only true if you have inertial observers, if you are talking about inertial frames, because if you are in a non-inertial frame, you can very easily observe the acceleration of an object to be non-zero, even though it's not interacting with anything else. So this idea that forces or interactions lead to accelerations is really only true if you restrict yourselves to frames, to observers, such that Newton's first law is valid. Okay, so Newton's first law essentially says that there are special observers called inertial observers, or there are special frames called inertial frames, in which essentially objects at rest remain at rest, in which objects moving at constant velocity keep on moving at constant velocity, provided that that object is not interacting overall with anything else. Okay. If that is true, then you can make the connection between forces and accelerations. Okay. And it's the job of Newton's second law to make that connection, to make this connection quantitatively precise, so that you can predict stuff. Okay. So here is Newton's second law. And first I'll spend around 10 minutes talking about where in the world does this come from. What do we mean by F? What do we mean by M? I hopefully do not need to spend too much time on what do we mean by A. That's the acceleration. Okay, and I also don't need to spend too much time on why is there an arrow on top of A. That's because acceleration is a vector. Okay, and then of course I do need to talk about why there's an arrow on top of this F, and why is there no arrow on top of this M. Okay, so I do need to talk about that. Okay, so let's get started. Essentially, this F, called the force, is basically a precise quantitative measure of interaction. The more strongly some object is interacting with something, we say essentially the more the force that this object exerts on the object that it is interacting with. Okay, so basically F is a measure of interaction. Okay. It's essentially, if I ask you what is a force, you can of course say the rate of change of momentum, but that's basically Newton's second law. You haven't really given me anything new. Okay. If you really want to talk about what is a force, really a force is basically an interaction. It's basically in some sense pushing or pulling. You interact with different objects by pushing or pulling on them. Okay. Almost always in this course you'll be interacting with objects by touching them. The only exception would be gravity, because gravity can reach out and exert an interaction, exert a force, even though two objects are not touching each other. You throw this chalk up in the air, this chalk of course, oh, my Pakistani team ka ban gaya hu, okay. You throw this chalk up, ये लाइटें पा रही है असल में. देखो वो पाकिस्तानी टीम की तरह मैं भी यूं बहाना मारूंगा कि देखो आंखों में लाइट पा रही थी, okay. But anyway, you throw this chalk up, the chalk is not touching anything else, neglecting air resistance, of course, is touching the air molecules as it goes up, but neglecting that, it's not touching anything else, and yet the Earth is able to reach out and pull down on it. That's what we mean by action at a distance force. Action and distance forces are essentially non-contact forces. You don't need two things to be touching each other in order to have a force. So gravity is is action at a distance. Force is a non-contact. Force is basically the only non-contact force that you see in this course, okay, that you see in basic mechanics. All other courses are because of two objects are literally touching each other. So if you are pushing a box, the box accelerates because you are literally touching the box, and then you are able to exert a force on it. Okay, right? So this F is basically a quantitative measure of this push or pull. Essentially, this measure of this interaction. Okay, what is this M? This M essentially is resistance to motion. Mass is a measure of inertia. That's literally what we mean. Okay, inertia is a resistance to motion. So mass is a measure of resistance to motion. Okay, how exactly is it resistance to motion? You'll see. Okay, but if you want to quantitatively talk about कौन सी इतनी fascinating चीज शेयर कर रहे हो क्या? If you want to quantitatively talk about force, the first thing I need to do is to first of all devise some way that I can exert this force in a controllable way, controllable, reproducible way. Okay, that's the very basic thing that you learn when you start doing experiments. Okay, if you want to investigate something, you need to study it over and over again, and you better make sure that you can control that thing. Okay, you can control as you have some idea about how big that thing is. You can control, you make it small, you can make it large in some quantifiable way. Okay, so the easiest way to do that in this context would be that okay, you take a block and you attach to the block a spring, and then you pull this spring. The more you pull this spring, the more you observe. If you pull it that way, the more you pull this spring, the more you observe the block to accelerate to the left. Okay, because the more you pull the spring, it turns out the more you are pulling it, aka the more force you are exerting on this block. Okay, and the extension of the spring gives you some idea on how hard you are pulling the block. Okay, so that's the advantage of doing it with a spring, because you can then immediately quantify that essentially how hard am I pulling it. Okay, if you pull the spring by 1 centimeter while the block is accelerating to the left, then of course you are exerting a smaller pulling force compared to if you pull it by 2 centimeters, for example. Okay, so you have this spring and you pull the spring gets stretched slightly, and then the block of course accelerates to the left if you are pulling the spring that way. Okay. Okay, what's the advantage of this? Because then we can study what happens to the block. The only thing I can measure over here right now is A. I don't know how to measure F, I don't know how to measure M. Okay? Then what do? I say, okay, first of all let's try to come up with a scheme that allows me to measure M, that allows me to measure mass. I've just given it a name, that M is mass. M basically tells me about the resistance to motion. The more M an object has, the more mass an object has, the smaller the acceleration of the object. That's what we mean by resistance to motion, that the acceleration of the object for a given force should be small. If your mass is bigger, the smaller the acceleration for the same force. Okay? So how do I control this mass over here? You take another copy of exactly the same block and you attach it to the top. You literally glue it so that there is no sliding between the two blocks. But now it's reasonable to assume, because they are the exact same copy, it's reasonable to assume that okay, if this was of mass m, the whole block now is of mass 2m. You pull the spring by exactly the same amount. That makes sure that you are exerting the same force always. So if you, with only this, you were pulling the spring, you were giving the spring an extension of 1 centimeter in order to pull this block to the left. Now with this copy attached, you again pull it by exactly 1 centimeter. That makes sure that you are essentially pulling it by exactly the same amount, by exactly the same force to be precise. What you observe then is that with this mass doubled, the acceleration is halved. You can attach another copy, and you can literally do these experiments. Okay, you now find that the acceleration is now 1/3 of the original acceleration. So what you have then is that the acceleration is inversely proportional to this quantity that an object has, this intrinsic quantity that an object has that tells you about how hard it is to accelerate a given object if you apply a force on it. That's that. Okay? And this, believe it or not, this very simple observation allows you to measure mass. It gives you an idea of what is mass quantitatively. Yes, it is a resistance to motion, but that is no good if I ask you to measure mass. If I give you one block and I say measure the mass of this, you cannot just say that okay, it's the resistance to motion. That doesn't give you a number. How do you get a number? If I ask you measure a length, how do you do it? You scale. Okay, so you essentially compare the unknown length to 1 meter. And what is 1 meter? 1 meter is some arbitrary length that we have declared कि इतनी length 1 meter. You could have chosen some other length and declared that to be 1 unit. That was perfectly fine as well. Okay, in olden times, of course, whenever the kings used to change, you had a new measure of length, okay, because every king had a different arm length, okay, and a different length of their feet, okay, so it was ridiculous, okay. So anyway, so now it's standardized. But still, that okay, this much length is 1 meter. People have arbitrary said. Not exactly this, but essentially they defined it as in terms of the distance that light travels in some interval of time. And that is always the same. Okay, so they have defined, they could have chosen some other interval of time that light travels in and defined that to be 1 meter. Then of course you would have a different, you would have probably have a longer, longer standard unit of length. The point being that you always, whenever you declare that, whenever you measure length, you are comparing it to some standard length. You are comparing it to 1 meter, which you have arbitrarily defined that this much length is 1 meter. Every other length will be measured as multiples of the standard length. You measure mass in exactly the same way. You declare that some mass is a standard mass, and you declare that the mass of this standard mass is 1 kg. Every other mass will then be measured by comparing it with this standard mass. You always do this whenever you have, that's exactly what the system of units means. You have 1 second, you declare some interval of time to be equal to 1 second. Every other interval of time is measured by comparing it, that how long was this unknown interval of time compared to the standard interval that you have defined. Okay? So this allows you to do that. You take essentially some block, okay, and you declare that the mass of this block is 1 kg. So you take a standard block. Okay, so what you do is that you have, first of all, take a standard block, you call it standard block, okay. You attach it to attach a spring to it, and you pull the spring by say 1 centimeter, 2 centimeters, whatever, and you measure the acceleration of the standard block, call that AS. The mass of this standard block is ms, which of course will set equal to 1 kg. Okay? And this says that for the same force, the product of mass times acceleration is a constant. Okay? That's obvious from Newton's second law, but remember I haven't reached over there yet. मैं उसको kind of motivate कर रहा हूँ उसी के लिए, okay? So so essentially, if the acceleration is inversely proportional to the mass, the product of the acceleration and the mass should be a constant. That's exactly what I'm going to use over here. So then you take an unknown block, जिसका आपने mass measure करना है. Say इसका mass unknown जो है, you attach the same spring to it, extend it by the same length, so that you are applying the same pulling force on this unknown block, and you say इसका mass mu है, unknown mass, इसका acceleration au है, the acceleration of the block with unknown mass. And what we have immediately is that MSAS should be equal to MUAU. It's as simple as that. And therefore, the mass of the unknown block equals AS over AU times ms. So now you know how to measure mass. You take one block, you say you declare the mass of this block to be 1 kg. You attach a spring to it, extend it by some distance by pulling it, and you measure the acceleration of the standard block. That gives you AS. Then you take the same spring, attach it to the block of unknown mass, stretch the spring by the same amount as you did for the standard block, measure the acceleration of this block of unknown mass. That's AU. And you immediately have mu, because then you declare that ms, I define the mass of the standard block to be 1 kg. So mass is literally, in some sense, the ratio of accelerations, as you can see over here. That's literally what it is. It's built into, that's basically a quantification of this weird statement that you memorize in O levels, A levels, metric FSE, that mass is a measure of inertia. That is the quantification of that. When we say inertia, we're talking about accelerations. How hard it is to change the state of motion of an object. What quantifies that? Change of motion, acceleration. Okay. Of course, I'm not saying that you measure every single unknown mass by pulling them, by attaching a spring to them and pulling them. So for example, if I ask you what's the mass of Mount Everest approximately, you don't go and attach a spring to Mount Everest and try to pull it. This is an operational definition. This is a start. In most cases, you measure masses by indirect means. This just gives you just a fundamental understanding of what we mean by the mass of an object is 60 kg or 70 kg or whatever. That compared to this standard block, if you have a mass of 60 kg, it's 60 times more difficult to accelerate u compared to this standard block. That's what we mean. Okay? And that exactly was essentially how mass used to be defined. There was a cylinder of metallic alloy which they kept in controlled conditions somewhere in France. Okay, बड़ी ख्याल से उसको निकाला जाता था दस्ताने पहन के. Okay, बाहर के कुछ सिलेंडर को प्यारे सिलेंडर को कुछ हो ना जाए. Okay, ताकि वरना फ्रूट सब्जी वालों को बड़ा मसला पड़ जाएगा. Okay, okay, so and then that's how it was done. Then of course 4 or 5 years ago they have changed to basically defining mass, measuring mass on the quantum mechanical scale. So now it's done in terms of the Planck constant, but the basic idea remains still the same. That if you say that mass is a measure of inertia, that's the quantitative understanding of what we mean by that statement. Okay. If I say that you have a mass of 80 kg, that means that compared to the standard block or standard cylinder, you are 80 times more difficult to accelerate. So if you are sitting there, it's much more difficult to get something useful done from you compared to this cylinder, which of course has served a very, very important purpose. Okay, but anyway, okay. So you have that. Okay, so mass you can now literally see is basically the ratio of two accelerations. Okay, so yeah. Hopefully now that statement is clear that mass is a measure of inertia. You can quantify that. You can precisely quantify कि इसका मतलब क्या है exactly. Okay. So now we have some idea of what this symbol is. Okay, sir, what is mass? Higgs boson or ye wo, okay. You can talk about that. That answers a different question. That why does an object have mass to begin with? That's the answer provided by the Higgs boson that's the question to which the Higgs boson provides the answer to. Here I am basically asking that how do you measure mass? To give you some idea about what mass is. Okay, so this is not a philosophical contemplation. It of course is very, very practical. Okay, right? Now again, you don't measure masses most of the time using this, but this gives you an idea of what mass is. If I say that okay, measure the mass of your friend, you don't push that friend and then measure the acceleration of your friend. कि क्या होता है उसे? Okay, you ask your friend, how weight scale पे खड़े हो? You basically measure the normal force, and that basically allows you to deduce the mass.
ये approximate है.
क्या approximate है?
ये जो mass आएगा weight.
Yeah, essentially yes. Okay, but to a very good approximation, basically the same thing. Okay, you deduce the value of m indirectly. Okay. वो approximate इसलिए because the earth घूम रही है and so on and so forth. Okay. Anyway, again this refers nothing whatsoever to the gravitational force. So this is true in deep space as well and so on and so forth. Okay. So don't confuse this idea of mass with a force. Okay. Now I ask, how do you measure force? Well, you say, okay, given a block, now what do I do? अब मैंने एक स्टडी करना है कि डिफरेंट फोर्सेस के साथ इस ब्लॉक को क्या होगा. तो what do I do? That's one way to do it. But maybe you say कि भाई ये प्रॉपर्टी स्प्रिंग की चेंज हो जाती है अगर मैं 1 सेंटीमीटर को या 2 सेंटीमीटर से पुल करूँ. आपने तो माशाल्लाह से बड़े पता नहीं क्या का कचरा याद किया, वो इलास्टिक लिमिट और प्लास्टिक लिमिट और हुक्स लॉ ब्रेक डाउन हो जाता है और ये वो मे बी उसका वो इलास्टिक लिमिट 1 सेंटीमीटर है, सो दैट द स्प्रिंग एक्सर्ट्स अ डिफरेंट फोर्स इफ यू स्ट्रेच इट बियॉन्ड 1 सेंटीमीटर. बट हाउ डू आई मेक श्योर दैट आई डबल द फोर्स? नहीं हाइट से तो फिर ग्रेविटी भी ले आए हो ना. 2 स्प्रिंग अटैच कर दो यार and stretch both of them by exactly the same distance. Then you are guaranteed that the force will be doubled. So you basically attach a spring over here and then you attach a spring over here and make sure both of them are stretched say by 1 centimeter. ये तो आपके A level का पेपर 5 का क्वेश्चन है यार. I think पेपर 5 ही था. Okay, yeah, okay. Long time ago for me. Okay. डायनासोर का ज़माना है मेरे लिए तो. अच्छा, anyway, okay, so that's how you do it. Okay, you attach 2 springs. If you want to triple the force, you attach 3 springs, and this basically immediately gives you an idea about why is there an arrow on top over here. If you attach 1 spring over here and 1 spring over there, and you stretch both of them by the same distance, क्या होगा? Block move ही नहीं करता. That means that for these interactions add like vectors. The direction matters. Okay, right. Anyway, and this m is not a vector. That also you can experimentally deduce. Okay, m basically just tells you about the resistance to motion in any direction whatsoever. आप d स्पेस में जाके आगे की तरफ धक्का दो, उस तरफ धक्का दो, ऊपर धक्का दो, नीचे धक्का दो, the ratio of the accelerations turns out to be the same in all directions. There is no special direction, so that's why it's a scalar. Okay, of course, near the surface of the earth, the symmetry is broken due to gravity. आप किसी कोई ऑब्जेक्ट है उसको ऊपर की तरफ धक्का देना डिफरेंट होगा कंपेयर टू आप साइड पे धक्का दो बिकॉज देयर इज ग्रेविटी. हाँ, फ्रिक्शन वो इसलिए मैं डीप स्पेस में गा रहा हूँ ना, फ्रिक्शन को तो अभी इग्नोर कर रहे हो ना. इस केस में
नहीं, लेकिन फ्रिक्शन वैसे इन एनी डायरेक्शन कॉज हो सकती है, ऑपोजिट डायरेक्शन ऑफ मोशन. तो फ्रिक्शन भी स्केलर.
वेल, मोशन की बात होती है, उसकी तरफ आ रहा हूँ. फ्रिक्शन स्केलर नहीं होता. ओके, उसकी तरफ आ रहा हूँ. ओके, फ्रिक्शन डजंट ऑलवेज अपोज मोशन सो टू स्पीक. फ्रिक्शन ओनली अपोजेज रिलेटिव मोशन. देयर इज अ बिग डिफरेंस. ओके, उसकी तरफ आएंगे. अगर फ्रिक्शन अपोज कर रहा होता तो आपकी गाड़ी ना चल रही होती. योर कार ट्रेवल्स फ्रॉम पॉइंट ए टू पॉइंट बी बिकॉज ऑफ फ्रिक्शन. वो फ्रिक्शन की वजह से एक्सलेरेट करते हैं. इंजन नहीं आपका एक्सलेरेट करता गाड़ी को. शॉकिंग न्यूज फॉर यू. इंजन सिर्फ आपके टायर्स घुमाता है. दैट्स ऑल इट डज. ओके, एनीवे.
सर, अगर बाय डेफिनेशन मास इज द रेशियो ऑफ द एक्सेलरेशंस तो फिर वो भी तो वेक्टर
नहीं, रेशियो ऑफ मैग्नीट्यूड ऑफ द एक्सेलरेशन राइट. ओके, हाँ, क्या चीज? mu is the unknown mass, s is the standard mass, as is the acceleration of the standard mass, au is the acceleration of the unknown mass. Okay? Okay, so you have a controllable way to change your force. And now आपने ब्लॉक नहीं चेंज करना. फिर दिस इज जो आप एक्सपेरिमेंटल डिजाइन होता है आपके इधर 3 वेरिएबल है. यू सिंप्लीफाई द सिचुएशन, यू कीप 1 वेरिएबल कांस्टेंट. वरना तो आपका मल्टी वेरिएबल फंक्शन है. अदरवाइज आप मास और एक्सेलरेशन दोनों चेंज कर दो, देन यू आर टॉकिंग अबाउट द डिपेंडेंस ऑफ फोर्स ऑन 2 थिंग्स. You keep one of those things constant and only change one at any single time. So here I am going to keep the mass constant. As in block को मैं नहीं change करता. Block वही का वही हमेशा लेता हूँ. I just attach different number of springs to it. So, okay, so if I take these 2 springs pulled by that, I find that the acceleration now is doubled. So I say, okay, that this pulling strength, this pulling interaction, I quantify it by this symbol F. And what I have done is that the acceleration is proportional to F. That's what I have experimentally found. Okay, अभी मैं vectors की तरफ नहीं जा रहा, I'm attaching springs, all of them to one side. Okay. And then I also know that the acceleration is inversely proportional to m. If I keep the force constant, the acceleration is inversely proportional to m. If I keep the mass the same, the acceleration is proportional to f. I can combine these two to write that the acceleration is proportional to f. लेकिन अभी तक मुझे measure करने का एक number deduce करने का तरीका नहीं मिला, a number corresponding to f. I know how to calculate a number for a. I know how to calculate a number for m. I don't yet have a way to calculate a number for f. And now I'm going towards that number. कि number निकालोगे कैसे? Well, from this, you can straight away write down that the acceleration is equal to some constant, the constant of proportionality, times f over m. And you can rearrange this to tell you that the acceleration equals, that the force equals 1 over c times ma. But 1 over c, of course, is some other constant. Since c was a constant, 1 over c is also a constant. Let's just write this as kma. So how will I then find k? नहीं इधर भी आपके पास है ना, यूनिट अब आप सेट कर रहे हो f के लिए. So you say some force, you declare कि कोई force है, उसको मैं declare कर देता हूँ 1 Newton. But this gives me a relation to do that. I declare that you have a force of 1 Newton when if this force acts on a mass of 1 kg, that mass experiences an acceleration of 1 meter per second square. If I do that, then of course I get 1 is equal to k times 1 times 1. And in this declared way of measuring force, k equals 1. तो फिर आप लिखते हो, okay, with this system of units, where I'm measuring now forces in newtons, where 1 Newton of force is the force that a mass of 1 kg requires to undergo an acceleration of 1 meter per second square, then I can write f is equal to ma. But now I say that, okay, if I attach the spring or two springs on different sides, the block doesn't accelerate, and therefore force is a vector. You have to add these forces not in magnitude but in terms of taking the directions into account. If I take essentially a spring like that, it turns out that only this component of this force will contribute. Okay? And you can do lots of different tests. It's basically that you have to cater to the directional nature of this force. And remember, forces are essentially just quantitative ways of quantifying the interactions. Okay? So f should be a vector, and the direction of the acceleration is the same as the direction of the total interaction or the total force. And this immediately then leads to that. Okay? तो हजरत न्यूटन ने हवा से नहीं लिख दिया था. Okay? He did not sit beneath an apple tree, झोली मलंग बंद के झोली फैला के, okay, आंखें बंद करके यूं सारी ला के बाबा बाबा नहीं गा रहा था या जो भी. Okay? He actually spent many years thinking about these things. Okay? Okay. Before we go on, of course, the next thing we have to do is to make ourselves comfortable with this. अभी तक तो मैंने आपको बताया कि आया किधर से है. Next, I need to tell you, of course, what is it good for, and to convince you that it's good for a lot of many different things. Okay, but before I do that, I feel I should talk somewhat about Newton's some things about Newton's third law, and then we can discuss the applications of Newton's second law and third law together, rather than because it becomes a bit difficult, it becomes a bit tricky to discuss only Newton's second law. That discussion is best done if you do it side by side. Okay, so Newton's third law is, the idea is very, very simple. Where does Newton's third law come from? कुछ तो सोचा होगा यार इसके बारे में. Otherwise तो आप फिजिक्स की बुक को जो पता नहीं लियो टॉल्स्टॉय का नॉवल बना के पढ़ते रहे हो क्या? कुछ तो सोचा होगा यार कि न्यूटन्स थर्ड लॉ किधर से आता होगा. Why does it make sense? चलो आता किधर से? Why does it make sense? Why does it seem like a sensible thing to believe in?
Observation.
That's one way, but even without observation, why does it seem like a sensible thing to believe in?
Balance in the word.
Yeah, but there is a lot of asymmetry in the word as well.
Balance.
There is a lot of asymmetry in the void as well. I mean, equal forces don't lead to the same effect. So, F is equal to ma. This is the cause of acceleration, and this of course is the effect. And the relationship between the cause and the effect is dictated by m. The bigger the mass, the smaller the effect. So, if you throw this chalk upwards, this earth, the whole of the earth is pulling down on the chalk. That's another story which we'll come to very soon. Okay, how did Newton deduce that? But then, if you believe in Newton's third law, this chalk also pulls up on the earth by exactly the same force. So, there is symmetry there, but then there's immediate lot of asymmetry. There's immediately a lot of asymmetry, because the effect of this force that the chalk exerts on the earth is infinitely small, because the mass of the earth is so big. The effect of the earth on this chalk is very, very big. You can see it with your own eyes. This chalk is initially going up, then it starts coming down. Why? Because the earth is exerting a force on this chalk. So, equal forces does not mean equal effects. Okay, so वो ठीक है, आपका सिमिट्री होनी चाहिए, पर सिमिट्री से सिमिलरली लॉ ऑफ ग्रेविटेशन की बात कर दो यार. लॉ ऑफ ग्रेविटेशन तो आपका स्फेरिकली सिमिट्रिक है ना, इट्स 1/r². You have the earth, for example, आपका ऑब्जेक्ट इधर है या इधर है या इधर है या इधर है, it doesn't matter as long as this object is the same distance away from the earth, is exactly the same force. And yet you can have all kinds of orbits around the earth. आपका elliptical orbit हो सकता है, मतलब जरूरी नहीं आपका spherically symmetric orbit हो. You can have all kinds of orbits. So, just because you have symmetry in the underlying laws does not mean that you have symmetry in the effects as well. तो फिर क्यों believe करते हैं न्यूटन साइड लॉ पे? Why is it a sensible thing to believe in?
Sir, because forces can occur between two objects.
Forces are between two objects, yes. तो फिर
एक ही object से कोई force नहीं लग सकता है और object.
yes, that's a start. Yes. So essentially it's basically there. अब किसी से हाथ मिलाते हो, अगर आपने उसके साथ हाथ मिलाया ऑटोमेटिकली दूसरे बंदे ने तो आपके साथ हाथ मिला लिया ना. इट्स लिटरली एज सिंपल एज दैट. आप अकेले तो नहीं हाथ मिला सकते, ऑफ कोर्स आप ये कर सकते हो, बट देन एक हाथ आपका दूसरे हाथ से जुड़ा हुआ है तो दूसरा हाथ पहले हाथ से जुड़ा हुआ है. ओके, यू कैन नॉट हैव फोर्सेज इन आइसोलेशन. Newton's proposal, of course, was that the interaction strength is the same, which kind of also makes sense. जितनी interaction तो इन दोनों के दरमियान exist करती है, whichever party you look at, you'll get the same interaction strength. That's the intuition. If you go to the quantitative analysis, it turns out that you need the two forces to be equal. Otherwise, you don't have, for example, conservation of linear momentum. You don't have the internal consistency of the theory. What I mean by internal consistency of the theory is that कि अगर एक problem मैं आपको दूँ और example मैं करवाऊँगा आपको अगली class में, you can solve the same problem involving Newton's second law in two different ways. If you don't have Newton's third law, you'll get two different answers. Okay? So you do need it for the internal consistency. That's what I mean. Okay? Internal consistency means that if you solve a given problem in different ways, you should get the same answer. Otherwise, your theory is not consistent. It's not self-consistent. Okay? Anyway, so Newton's third law, of course, अगर मैं statement आपसे पूछूं, आप कहोगे equal, every action is an equal and opposite reaction. Right? ये आपका favorite statement. I really hate that statement. Okay? Don't get me started on that. Okay? Because you have to be much more precise. Okay? इसलिए. Okay? क्योंकि ये अगर आप statement सिर्फ याद करोगे 10 दफ़ा गलती करोगे और एक दफ़ा जो है ना, even a broken clock is correct twice a day. Okay? So you have to be much more precise when you do it. Okay? If object A exerts a force on object B, then object B exerts an equal and opposite force on object A. Why am I making this distinction very clearly? ये जो आपका F is equal to ma है, this F is talking only about the forces acting on the object of mass m. It makes no reference whatsoever to the forces exerted by the object. आधी क्लास मुझे पता है न्यूटन थर्ड लॉ की वजह से वो फोर्सेस कैंसिल करके बैठी होती है. If you are walking, you push back on the ground pushes forward on you. That's why you are able to walk. These two forces do not cancel because one of these forces is acting on the ground The other force is acting on you, different objects. This F only talks about forces acting on an object, that's it. One of these forces was being excited by the object, not on the object. Only one of these was on the object. The force exerted by the ground on you. The force that you were exerting on the ground goes into the application of Newton's second law to the ground, not on you. Okay? So just remember, action and reaction forces must act on different objects. तो आप याद कर सकते हो क्या? Every force has an equal and opposite reaction force, every action has an but add to that the qualifier that the action and reaction forces must be on different objects. अभी मैं एक एग्जांपल कराऊंगा जिसमें आधी क्लास गलत करके बैठी होगी. ओके, कम से कम दूसरे सेक्शन में तो तकरीबन सारों ने गलत किया था. ओके, बट एनीवे, ओके, सो टू get then comfortable with this, we need to get comfortable with this. We need to essentially get comfortable with the different kinds of forces that you can have. Any given problem that involves the application of Newton's second law, the idea is that given the interactions, you basically imagine what kind of interactions are at play. Once you have those interactions, you have to deduce the accelerations. Once you have the acceleration, you can then deduce the position of the object. ये जो आखिरी पार्ट है वो हमेशा from now on वो मैं छोड़ दिया करूँगा, unless I actually need it to solve the problem. वो मैं assume करूँगा कि आपको इतना आ गया है. The whole of kinematics is basically going from acceleration vector to position vector. तो वो तो आपको I assume कि आपको आता है. How justified am I in that assumption is very questionable, of course, but ignorance is bliss. Okay, but anyway, for me, not for you. Okay, आपके लिए तो कुछ ज़्यादा ही bliss है. Okay, but anyway, okay, so you have to get comfortable with different kinds of forces at play. The very first obvious force that you see all around you is, of course, the gravitational force. Now, what Newton proposed was near the surface of the earth, first that near the surface of the earth, every object is being pulled down by the earth. Okay? And he wrote down a law that describes that describes this force even when the object is not near the surface of the earth. He wrote down, of course, that F is equal to capital G times m over r square. Yeah, मैं magnitude लिख रहा हूँ, hence I didn't put a vector. Okay, so he basically proposed, he gave a hypothesis essentially. Once you test hypothesis enough number of times, it becomes a law, of course. He basically hypothesized that any two masses, now you have an idea what mass is, but then he hypothesized that any two masses exert a force on each other of that magnitude. Basically, the force is proportional to the product of the masses and inversely proportional to the square of the distance. अब ये हजरत न्यूटन को पता कैसे चला था? कि तुक्का मारा था या झोली लेके बैठ गए थे, क्या किया था?
एक्सपेरिमेंट किया था.
नहीं, एक्सपेरिमेंट नहीं किया था. That was one start, but Kepler law की जरूरत नहीं थी उसे. Kepler's law तो बाद में he was showing off when it came to Kepler law. He already deduced this without Kepler's laws. So Kepler's laws basically tell you how do planets move around the sun. They are basically quantitative statements that describe how exactly do planets move around the sun. They move in elliptical orbits. उनके time period की क्या relation है orbit parameters के साथ blah blah. Okay. He did some very simple calculations. कैसे deduce किया था?
F को mg के बराबर
जी क्या?
9.81 या 10.
लेकिन वो किधर से आया? इधर तो mass of Earth भी है. Okay, so this is how he deduced it. Okay. अब गौर से सुनना पूरी कहानी. Okay. So he first of all he knew one thing from Galileo, of course, and that people started believing in around his time, is that every object, no matter what its mass is, once you drop it, it experiences the same acceleration downward. So his first idea, and that's why it was called the law of universal gravitation, his first idea basically was that he really believed that the force that is responsible for pulling down, for making objects fall near the surface of the earth, is the same force that is responsible for keeping the moon in orbit around the earth. It's the same force that is responsible for keeping the earth in orbit around the sun. It's basically the same force manifesting itself at different length scales. Okay, so he can deduce properties, some properties of this force by looking at what happens near the surface of the earth, and some properties by looking at what happens on bigger scales. That was his first idea. Okay, because he believed that it's the same force. कि उसके कुछ aspects में इधर से ले लेता हूँ, कुछ aspects उधर से ले लेता हूँ. Okay, then he said that okay, your objects of different mass undergo the same acceleration. Why are they falling to begin with? Because of this force. And he knew that the force equals ma. If this a is independent of m for a falling object, f के अंदर भी तो small m होगा. This m must cancel. Otherwise, this a would not be independent of m. So he immediately deduced that this f should contain m, the mass of the falling object. Okay. Then he said, okay, that the force is proportional to the mass of the falling object. And then you say that, okay, Newton's third law के मुताबिक, essentially, so by symmetry, essentially, first of all, you can say that, okay, okay, now let's not go there, okay. You can then say that by Newton's third law, the force that the earth experiences should be proportional to the mass of the earth. कि कोई भी object जो है वो it experiences a gravitational force proportional to the mass of the object. If this is true for the falling object, it should be true for the whole earth as well. So the force that the gravitational force that the earth is experiencing is proportional to the mass of the earth. Okay. But then by Newton's third law, the force that the earth is experiencing should also be proportional to the mass of the falling object. And again by Newton's third law, the force that the falling object is experiencing should also be proportional to the mass of the earth. So this force should contain the product of the two masses, the mass of the earth and the mass of the falling object. Okay. So आपका जो falling object है उस पे force is proportional to the mass of the falling object, right? Then the force that the earth experiences is proportional to the mass of the earth. Then by Newton's third law, क्योंकि mass जो force लग रही है object के ऊपर, falling object के ऊपर, उतनी force लगनी है earth के ऊपर. So if this force is proportional to the mass of the falling object, the force on the earth is also proportional to the mass of the falling object. But then we also have argued that the force on the earth is proportional to the mass of the earth. So the force on the earth is proportional to the product of the two masses, and therefore by Newton's third law, the force on the falling object is proportional to the product of the two masses. Okay, देखो कितनी simple सी mathematics है, okay, लेकिन reasoning जो है अभी तो कुछ भी नहीं उसने किया start. Okay, then he said that okay, the force is proportional to that. Then of course he had this idea that this force, again like I said, is the same force that is responsible for example, keeping the moon in orbit. He was really fascinated by the moon, by the way. उसकी simple सी वजह ये थी because measurements of the moon, the orbit of the moon were quite reliable in those days. वो जो measurement of the distance of the earth from the sun वो इतना reliable नहीं था. So of course he has to formulate a theory. He needs some experimental data. वो experimental data उस ज़माने में क्या होना था? The orbit length essentially, the radius of the orbit. The moon, incidentally, the orbit of the moon to an excellent approximation is basically a circle. To make the reasoning even more simple, ellipse की बात ही नहीं उसको करनी पड़ी. Okay. Most orbits are actually elliptical. वो अगली दफ़ा मैं आपको दिखाऊंगा simulation करके कि you don't just have circular orbits. उसका भी उसने experiment वो सोचा था कि क्यों होगा. अच्छा, anyway. So he basically had this idea that okay, this force should essentially, when it reaches out and exerts an influence, its strength should decrease with distance. Okay. क्योंकि essentially it's the same force that is responsible for keeping the moon in orbit that is responsible for making objects fall down near the surface of the earth. Okay. Moon पे उसका idea था कि moon पे कम force होगी compared to an object near the surface of the earth. Okay. That was his guess. अभी उसने क्वांटिफाई करना है. सो देयर सम फंक्शन ऑफ द डिस्टेंस बिटवीन द ऑब्जेक्ट्स. उसको नहीं पता ये फंक्शन क्या है एग्जैक्टली. मे बी इट्स 1 over r, मे बी इट्स 1 over r square. आपको तो पता है कि 1 over r square उससे डिड्यूस किया था इवेंचुअली, बट राइट नाउ इट्स सम फंक्शन. And then of course you can just write down that this is some constant times m and then some function of r. अब उसे डिड्यूस करना ये फंक्शन है क्या. Of course here उसने कोई जनरल नहीं रखा, उसने गैस कर लिया था स्ट्रेट अवे कि 1 over r square होगा. उसकी intuition, the intuition basically was that the gravity is basically spreading out over spheres. So as you go out, the surface area of a sphere increases as r square. अगर एक बल्ब एक रखा हुआ है आपने, you go further away, a distance r away, the intensity goes down as 1 over r square. If you imagine the influence of gravity to act in a similar way, the gravitational force should go down as 1 over r square. That was his guess. Okay? तो उसने जो है इधर लिख दिया कि मे बी क्वेश्चन मार्क परहैप्स. That's his guess. Okay? वो क्योंकि वो एक्सपेरिमेंटल डाटा से मैच नहीं करेगा. That उसने टेस्ट करना है अभी एक्सपेरिमेंटल डाटा से. ओके ओके अगेन उसने लिख नहीं दिया, उसने फिर टेस्ट वगैरह करना है सारा. ओके फाइन. सो यू हैव दैट एंड देन यू बेसिकली टेस्ट इट. तो सबसे पहले तो कहो हाउ डू आई यूज दिस टू एक्सप्लेन दैट ऑब्जेक्ट्स नियर द सर्फेस ऑफ द अर्थ आर फॉलिंग डाउन. वेल यू से ओके नियर द सर्फेस ऑफ द अर्थ आपका आर जो है बेसिक रेडियस ऑफ अर्थ है. His idea was that you measure distances of the object from the center of the earth. So near the surface of the earth you are just going to get gmm over re square, where re of course is just the radius of the earth. And this you can just write as m times g, where g you define to be gm over re square, which is some constant. And that we know. हमें g की numerical value पता है from experiment. So if you know g, you can actually find out the mass of the earth. लेकिन न्यूटन को g की वैल्यू इतनी प्रिसाइजली नहीं पता चली थी क्योंकि वो इतना अच्छा एक्सपेरिमेंटलिस्ट नहीं था. It was only some years later that Cavendish did the experiment, and उसने जो पेपर लिखा था उसका टाइटल ये नहीं है I'll measure g. He was more pompous than that. He'll say I'll weigh earth. Okay. So indirectly, if you know capital G and you know small g and you know the radius of the earth, you can deduce the mass of the earth. Okay. क्या चीज? वो तो एंशिएंट ग्रीस को भी पता था या इजिप्शियंस को भी पता था. यू बेसिकली आप इफ यू स्टडी शैडोज यू कैन डिड्यूस द रेडियस ऑफ द अर्थ. ओके गूगल करके देख लेना, देयर मेनी स्मार्ट वेज टू डू इट. ओके ओके आप एक कश्ती का जो वो पोल जो है वो नजर आ रहा है आपको, होराइजन से नजर आ रहा है, उसे भी आप डिड्यूस करते हैं. देयर मेनी वेज टू डू इट. ओके ठीक है. अच्छा एनीवे, so you have explained that that falling things near the surface of the earth undergo this acceleration. अब वो मून पे गया, not literally लेकिन मून के ऑर्बिट पे गया. ओके and he asked a very very simple question, जिसका मजे की बात है 5 साल के बाद फिजिक्स के बाद पढ़ने के बाद जवाब नहीं आता लोगों को. He asked a very very simple question. मून गिर क्यों नहीं जाता? Why doesn't the moon fall down towards the earth? ठीक है, तो सपोज करो ये अर्थ है और ये मून है, और सपोज मैं इधर कोई ऑब्जेक्ट छोड़ता हूं, इस ऑब्जेक्ट को क्या होगा? वो गिर जाएगा. अगर ये मून है तो वो क्यों नहीं गिरता? मैस उसका ज्यादा है. क्या है? दोनों केसेस में फोर्स एक ही जितनी है. जिधर मून है उधर ही आपने ऑब्जेक्ट छोड़ा था. तो द फोर्स एक्टिंग ऑन, अकॉर्डिंग टू दैट, द फोर्स एक्टिंग ऑन द मून एंड the object that you have released is exactly the same. लेकिन जो ऑब्जेक्ट जो आपने छोड़ा है वो नीचे आके गिर गया अर्थ पे. मून ऑफ कोर्स एक ऑर्बिट में चला गया. हाँ क्या चीज? वो तो अर्थ पे एक्ट कर रही है ना, तो वो अर्थ पे एक्ट करे. नहीं उस पे नहीं. अर्थ का मैस बहुत ज्यादा है कंपेयर टू द मून. अर्थ पे बहुत कम इफेक्ट होता है उस फोर्स का. वो बैलेंस आउट नहीं ना कर सकते बिकॉज दे एक्ट ऑन डिफरेंट ऑब्जेक्ट्स. हाँ उसका भी बहुत कम इफेक्ट होता है. एग्जैक्टली मून, द कंक्लूजन ही इमीडिएटली ड्रू वाज कि मून भी गिर रहा है, वो ऑब्जेक्ट भी गिर रहा है, दोनों गिर रहे हैं. The moon is also falling down, except that when the moon falls, what do you mean by falling down? देखो ये मून एक ऑर्बिट में है, थोड़ी देर बाद इधर है, ये इसने वर्टिकल डिस्टेंस नीचे नहीं किया. वो अर्थ की तरफ क्यों नहीं आया? बिकॉज द सर्फेस ऑफ द अर्थ, बिकॉज इट्स अ स्फीयर, हैज ऑल्सो कर्व्ड डाउनवर्ड्स. ये जितना डिस्टेंस है उतना ही ये डिस्टेंस है. वो अर्थ की सरफेस में तो कर्व कर गई नीचे की तरफ. द मून हैज ऑल्सो फॉलोन डाउन. ये देखो, ये आपका वेलोसिटी, ये इनिशियली मून यूं मूव कर रहा है, आपकी एक्सलेरेशन का क्या डायरेक्शन होगा? द सेम एज द ग्रेविटेशनल फोर्स. थोड़ी देर बाद वेलोसिटी वेक्टर का क्या डायरेक्शन होगा? ये द इनिशियल वेलोसिटी वेक्टर प्लस द चेंज इन वेलोसिटी वेक्टर. अब आपका मून इधर होगा, अब आपकी फोर्स यूं है, अब आपका यूं वेलोसिटी वेक्टर आएगा. एंड यू कैन इमीडिएटली सी दैट वो पूरा एक सर्कल बन रहा है. अगर आप ये कंटिन्यू करो एरोज को, मून भी गिर रहा है, बट द सर्फेस ऑफ द अर्थ इज ऑल्सो फॉलिंग डाउन, सो टू स्पीक. ओके, ये नहीं है कि एक केस में ग्रेविटेशनल फोर्स गिरा रही है, दूसरे केस में नहीं गिरा रही. इट्स नॉट लिटरली इंग्लिश लैंग्वेज टाइम्स में नहीं गिर रहा, बिकॉज द डिस्टेंस बिटवीन द अर्थ सरफेस एंड द मून रिमेन्स द सेम, क्योंकि अर्थ की सरफेस भी उतनी गिर जाती है. ओके, एनीवे, so what we have over here is that the moon does fall down some distance. इसको SM कह देते हैं. Initially distance इधर है, initially आपका मून, so just to clarify, ये मून का ऑर्बिट है, ये अर्थ है, थोड़ी देर बाद मून इधर होता है. ये मैंने बहुत एग्जैजरेट किया है बाय द वे. आपको सर ये थोड़ी देर बाद तो नहीं, ये तो आपने कोई ये 28 दिनों में पूरा चक्कर मारते तो आपने एक हफ्ता बना दिया. ओके, I've exaggerated the system, the situation. Okay, the moon falls down this distance SM. ठीक है, and I look for what SM is for a short interval of time. Why a short interval of time? क्योंकि short interval of time के लिए ये acceleration approximately constant होगी. I don't need to worry about then for a very short interval of time. You don't need to worry about कि acceleration का direction change हो रहा है. Yes, sure, it's towards the earth. लेकिन देखो initially इधर है acceleration, फिर इधर हो गया. Acceleration का direction तो change हो रहा है ना. But for a very short time interval, the direction of the acceleration vector is approximately constant. Okay. Now, for a short interval of time, SM मैं कैसे निकालूंगा? The acceleration is pointing downwards. The acceleration is approximately constant. The vertical velocity of the moon is, at this instant of time, moon यूं करके move कर रहा है. What's the vertical velocity of the moon? 0. तो vertical distance उसने क्या fall किया होगा moon ने? half gt square. जहां G क्या है? G is the gravitational field strength at the location of the moon, not near the surface of the earth. As in ये है G जो है वो है G, capital G times the mass of the earth divided by the radius square of the moon's orbit. So SM is nothing other than half times GM times delta T square. Delta T is the short time interval that we are considering. क्या चीज? ये तो वो तो बहुत ज्यादा लार्ज पे जाओ फिर शायद नहीं अप्लाई करती. बहुत हाई एनर्जीज पे भी जाना पड़ेगा. इतनी ये दिस इज नॉट लार्ज, इधर अप्लाई होती है जो वेरी वेरी गुड अप्रोक्सीमेशन. ओके ओके, सो वेयर GM from GM is just a shorthand for those constants. Okay, कि फोर्स क्या है? कि बेसिक फोर्स मून पे क्या लग रही होगी? G times capital G times capital M divided by the radius of the moon squared, by radius of the moon's orbit squared. और फिर जो है आप, okay, right, so this is equal to GM over RM square. RM is the radius of the moon's orbit. Okay, great. फिर उसने कहा okay, let me draw a connection between this and an object falling near the surface of the earth. अगर मैं near the surface of the earth एक object छोड़ूं from rest, vertical distance कितना fall करता है in the same time interval? कितना fall करता है? SO for object half times GO delta T square. GO of course is the gravitational field strength at the surface of the earth. तो GO किसके बराबर है? Is equal to GM over RE square. Okay, then he said let's measure the ratio. What is the ratio? This is equal then to basically you plug those things in. This is will be equal to half gm delta t square over half g naught delta t square. gm over g naught बच गया, लेकिन gm over g naught को फर्दर सिंप्लीफाई कर सकते हो क्योंकि देखो कैपिटल G और कैपिटल M तो सेम है, तो फिर क्या आएगा? You'll basically get you basically will get RE square right? Okay, अब उसके पास ये वाले नंबर जो है he can immediately find this number out because he has from data for the moon, he knows first of all the radius of the earth, he knew the radius of the moon's orbit. तो ये इसकी न्यूमेरिक, ये जो भी नंबर आता है उसे निकाल लिया, ठीक, फाइन. इफ दिस होल थ्योरी इज ट्रू, इफ ये आप वाकई 1/r स्क्वायर है, दिस नंबर शुड मैच दैट. अब ये नंबर वो कैसे निकालेगा? हाउ डू यू फाइंड दिस आउट? Distance fallen by the moon, distance fallen by an object near the surface of the earth. Okay, so SO कैसे निकालेगा वो? Right, you just study the motion of an object near the surface of the earth. उसको रेस्ट से छोड़ा है, देखो फॉर एग्जाम्पल के 0.1 सेकेंड में कितना डिस्टेंस फॉल किया, नोट दैट डाउन. वो तो ऑफकोर्स उसको पता था ऑलरेडी. ओके, SM कैसे निकालेगा? सिंपल ज्योमेट्री. ओके, ये देखो, ये आपकी अर्थ है, ये मून है, इधर मून इधर है, थोड़ी देर बाद इधर है. व्हाट डू यू गेट? यू आर बेसिक गेटिंग दिस आर्क. ये सर्कुलर आर्क बन रही है, ये RM है, ये RM है, दिस लेंथ इज RM, दिस लेंथ इज RM. ये एक एंगल स्वीप आउट हो रहा है थीटा. SM क्या है? ये वाला डिस्टेंस. SM इज सिंपली RM माइनस RM कोसाइन थीटा. टाइम इंटरवल डेल्टा टी में थीटा क्या होगा? वेल, उसको पता है कि लगभग 28 दिनों में एंगल आपका 2 पाई बनता है, तो 0.1 सेकेंड में एंगल कितना स्वीप आउट होगा? यू बेसिकली हैव एवरीथिंग. अब ये दो नंबर्स की रेशो ले लो, कैलकुलेट दिस रेशो, कैलकुलेट दिस रेशो, टू अ वेरी गुड अप्रोक्सीमेशन यू गेट द सेम नंबर. नहीं, बिल्कुल नहीं है, बट अगेन टू फर्स्ट अप्रोक्सीमेशन it's a pretty good approximation of perfect sphere here. Okay, it's slightly bulging at the equators, it's slightly squashed at the poles. वो अगेन क्योंकि वो रोटेट कर रहा है अपने एक्सिस के, इसलिए. हाँ, क्या चीज? अर्थ रोटेट कर रही है, श्योर, यस. तो बट ये तो मैं मून के ऑर्बिट को देख रहा हूँ ना. So I'm doing this whole calculation in the reference frame which is at rest with respect to the moving earth. Okay, वो of course वो अर्थ के रोटेशन के थोड़ा सा नॉन इनर्शियल इफेक्ट आता है, पर वो बहुत छोटा होता है if you actually compute it. Okay, right? So that's how you deduce Newton's law of gravitation. Again, to summarize, this is the easy part. Okay, why did he deduce this? Because he wanted to explain again essentially why do objects of different masses undergo the same acceleration when you drop them. It basically is an attempt to answer that simple question कि ये product of masses किधर से आया. And then the rest of the thing is to connect things that are happening near the surface of the earth to things that are happening way beyond the surface of the earth. कि वही फोर्स जो आपके चौक को नीचे खींच रही है, वही फोर्स आपके मून को ऑर्बिट में रख रही है. That's where this thing comes in. And then you propose कि शायद ये f of r जो है आपका 1/r square है. Does that hypothesis agree with observational data regarding the moon? The rest of it is just simple mathematics that shows you that. Okay? So अगर अब मैं पूछूं, हाँ,
Sir, included in this
हाँ, या तो इधर assumption उसके न्यूटन की ये थी कि he was measuring distances from the center of the earth. सबसे बड़ा उसको यही दाल में काला लग रहा था कि ये मैंने क्यों assumption मारा। आपने तो ऑफकोर्स रात को सो जाना है आराम से। उसको बड़ी बेचैनी थी, 20 साल तक बेचारा बेचैन रहा था इस बात के ऊपर। One big reason why he did invent calculus, one big motivation was precisely this, कि वो convincing answer देना चाहता था that essentially when it comes to measuring forces that are involved over there, you can essentially replace the whole of the earth by a single point particle at its center. Okay? वो उसकी डिटेल में मैं नहीं जा रहा, but you can prove it essentially कि आप सेंटर से करो। Okay? They are called shell theorems in case you are interested. Okay. So एक फोर्स हमने कर लिया ग्रेविटेशन, एंड होपफुली और कुछ नहीं पल्ले पड़ा। अगली दफा मैं सिमुलेशन भी आपको शो करूंगा। ही वॉज अ वेरी क्रिएटिव पर्सन। ओके, ये पेपर में आएगा, ग्रेविटी के बगैर पेपर आएगा आपका। अस्तगफिरुल्लाह, इसमें क्या मुश्किल था? क्या मैं लिटरली मैथमेटिक्स देखो, ये है, ये है, और ये है, और ये है। आई मीन इसमें कोई डिफरेंशिएशन नहीं की मैंने, कोई इंटीग्रेशन नहीं की। लिटरली x इज इक्वल टू हाफ GT स्क्वायर लगाया मैंने। नहीं तो आप फिजिक्स, क्योंकि आपने तो फिजिक्स सीखनी है ना। It goes hand in hand. Okay. Anyway, so now we have some idea about the gravitational force. Just remember that two masses exert a force on each other because of the fact that they have masses. Okay. The next force that we have to do is to, और अब मैं बड़े कॉन्फिडेंटली कर सकता हूँ, इस तो ये देखो चौक नीचे गिरा रहा हूँ, चौक नीचे गिरेगा और फिर कुछ देर के बाद क्या होगा? चौक को टूटने के बाद क्या होगा? रुक गया, ग्रेविटी ऑफ हो गई है? Of course not. Just because it's now in contact with the earth, it's reasonable to assume that of course gravity has not switched off. So why doesn't this chalk keep on falling down? So it's not falling down because then there needs to be an upward force. So as we go along in the next lecture, you'll keep on seeing new forces. Of course, आप immediately उसी वक्त ऑब्जेक्ट, सर आप जब भी कोई नया प्रॉब्लम आ रही है कि नई फोर्स इजाद किए जा रहे हैं, ओके। Well, the point is that the only limited number of different forces. थोड़ी देर बाद हम रुक जाएंगे नई forces इजाद करना, okay? Okay, so now I need to spend 5 minutes talking about this force, this other force that you have on the stationary chalk. Okay, so here's your ground. You have this object. इस पे क्या क्या forces लग रही हैं? There's the weight. And do not say normal reaction, okay? मेरा खून खोलता है, okay? Just call it the normal force. Do not call it the reaction force. बता रहा हूँ, okay? So first of all, ये एक force है N. अब ये किसकी reaction force है? पहले तो ये मुझे बताओ. The reaction force to the, इधर आपने identify किया कि ये action force है, ठीक है, okay, fine. The reaction force cannot be acting on the same object as on which the action force is acting. सेकेंडली n जो है उसका मैग्नीट्यूड भी जरूरी नहीं mg के बराबर हो। इस सिचुएशन में यस mg के बराबर है। ये डस्टर है, नहीं फेंक नहीं रहा, रिलैक्स करो। ये डस्टर है। आई एम पुशिंग दिस इनवर्स टुवर्ड्स द बोर्ड। व्हाट्स द नॉर्मल फोर्स नाउ? बाहर की तरफ। इसका तो ना डायरेक्शन वेट के सेम है, ना मैग्नीट्यूड वेट के बराबर है। The magnitude of this normal force depends entirely on कि कितनी जोर से मैं दबा रहा हूं डस्टर को। इसका तो वेट से कोई ताल्लुक ही कोई नहीं। It's just that in this stupid problem, coincidentally, the normal force comes out to be equal to the weight, इसलिए आप ही डिक्लेयर कर देते हो अपने बचगानापन में कि normal force weight के बराबर ही होता है। That's a very, very special situation. It's not true in general at all. Moreover, just to drive home the point कि normal force वेट के बराबर नहीं होता, they even have a different physical origin. Normal force आती किधर से है? That's a start. Normal force आती किधर से है? I mean, gravity का तो मैं आइडिया हो गया. That given that you have two masses somehow they are able to reach out and exert a force on each other, an attractive force on each other. Where does the normal force come from? थर्ड लॉ से नहीं आती. थर्ड लॉ से फोर्स कभी नहीं आ सकती. आई मीन फोर्सेस कम ड्यू टू इंटरेक्शंस. कौन सी चीज किसके साथ इंटरेक्ट कर रही है सच के नॉर्मल फोर्स बन रही है? इस बेसिकली जब आप अगर आप खड़े हुए हो, आपके ऊपर एक नॉर्मल फोर्स है, आपके जो जूते हैं दे आर लिटरली पुशिंग डाउन ऑन द ग्राउंड. कॉरस्पॉन्डिंगली जो जूतों के साथ कॉन्टैक्ट है ना ग्राउंड, corresponding that part of the ground is pushing back up on you. It's literally like standing on a mattress. घर में जाना, मैट्रेस के ऊपर खड़े होना, मैट्रेस को क्या होता है? थोड़ा सा खूब जाता है. थर्ड लॉ की वजह से फोर्स नहीं आती. थर्ड लॉ जस्ट गिव्स यू अ रिलेशनशिप बिटवीन टू फोर्सेस. थर्ड लॉ की वजह से आई मीन सिमिलरली MA डज नॉट लीड टू ए फोर्स. MA खुद एक फोर्स नहीं है. Which is why I hate the word centripetal force. Centripetal force खुद से force नहीं होती. Centripetal force just refers to the total force towards the center. वो अलग से एक force नहीं है. It's just a special name given to कि भाई एक net force है. Anyway, आप मैट्रेस के ऊपर खड़े होते हो, वो मैट्रेस खूब जाता है. क्यों? Because you are standing on the mattress. वो मैट्रेस नीचे आप you are pushing down on the mattress. The mattress once it's squashed down pushes back up on you. Literally the same thing happens when you stand on ground. Yeah, anything is on the ground. वो जो object है that is trying to push down on the ground pushes back up on that thing. Except फर्क सिर्फ यह है कि मैट्रेस का आपको डिप्रेशन जो है वो नजर आता है, ग्राउंड का नहीं नजर आता. Because the ground is essentially composed of extremely stiff springs. वो springs जो हैं ग्राउंड में बहुत ज्यादा stiff हैं, वो आपको नजर नहीं आता कि कंप्रेस हो रहा है. Okay, but it's basically the same thing, okay? Okay? So do not confuse the normal force with mg. Okay, chalo, jao. Chutti.